When we're looking at solids of known cross-section, what we're doing is we're using an integration technique where we have a region, and that region actually forms the base of the solid. And then we build vertically on that base with cross-sections that we know. So in this situation, I've set up cross-sections on top of that base that are squares. And each one of these squares, since it is a three-dimensional shape, it has in this situation it has an incremental width dx. So that ends up, then that incremental region right there ends up being a prism. And so if we take a look at that, then as we build these, stack these prisms up from the left to the right, these prisms get successively smaller since this distance that the function is from the x-axis at the base is decreasing. These incremental square prisms get tinier and tinier and tinier, and the solid is formed in that respect. Likewise, if I would take that same base, which is nothing more than a parabola in the first quadrant, and stack up square prisms and then stack them along the y-axis so that we have this incremental thickness dy here. Then I would stack these square prisms up from the x-axis all the way to that vertex of the parabola, and again those prisms would be getting successively smaller, and I could form a solid that way. And if you notice, depending upon the orientation of the slice or the incremental dx or dy, I get two very different volumes because of that different orientation. So if we take a look at this and remember from geometry that volume of a prism the volume of the prism is the area of the base times the height. Well, the area of the base of this prism is nothing more than the cross-sectional area of this square here. So in that situation, that area then is going to be related to that function, that parabolic, in this case, this parabolic function. So the area of that base is going to be nothing more than some sort of function in terms of either x or y. I'll go in terms of x here. And the height of this pyramid is nothing more than that thickness. And so the height becomes that incremental dx or dy. And so if this is the area of one of these prisms, then if we stack all the prisms up from left to right, and of course that's an accumulation process, which is where we get the integral sign from, then we can get an expression, a calculus expression, to find the exact volume of that solid. Likewise, if we would stack them up with the incremental along dy, then we would have a function in terms of y, and the thickness of each prism is now a dy, and we could get a similar expression. So, so those would be the two expressions, and again, you have to be real careful to make sure that you're using the right expression depending upon whether you're stacking perpendicular to the x-axis or perpendicular to the y-axis. Before we get into doing some calculus in regards to building volumes of known cross-sections, I want to go over some pretty basic cross-sections that you'd expect to see in your homework and on the AP exam. And I have the same quadratic as the base here. And I'm going to build each area with either semicircles, squares, rectangles with a certain proportion. We'll talk about that proportion when we talk about the rectangle expression. Or equilateral triangles. And so if we look at the algebraic expressions for each, and these are all built along the x-axis, so these are all going to be dx problems. If we look at a semicircle here, we know the area of a circle is pi r squared. So the area expression here would be pi r squared divided by 2. That would be your semicircle. There's your radius. And so if we look along the bottom of the semicircle here, which is the diameter, that diameter extends from there up to the function f of x. So we actually have an expression for the diameter. The diameter the diameter is f of x. Distance from the x-axis up to the function there. And the radius is half the diameter. So the radius is going to be half of the value of that function, no matter where we put this incremental dx, this incremental volume. So the expression for the area here for a semicircle in terms of the function is going to be pi over 2 times f of x over 2 squared. And simplifying that entire expression, we're going to have pi over 8 times the function squared. So there's an area expression as we build it along the x-axis. Going to the square, we know that the area for a square is side squared, so we're talking about the, if we call the edges of the square S, we're talking about side squared. And again, if we look at the bottom of the square sitting on that quadratic relationship, then this side is in fact the value of the function at any given point. And so the area for a square here is going to just be the function squared. So there's the area expression that you would put into the integral if you were dealing with cross-sections that were squares. If you're going to deal with cross-sections that are rectangles, you're going to need a specific proportion for that rectangle so you can get everything in terms of one variable. So if we have a height here, h, and we have a length here, L, we notice that that length relationship is actually the value of the function. So we have the length being the value of the function at any given point, and the height then is going to be half the length at any given point. So the height then is going to be the function divided by 2. And then once you have this appropriate proportion, you can go ahead and get your area expression for the rectangle, which is going to be length times height. And so that's going to be f of x times half f of x. And so that's going to be 1/2 f of x squared. For the rectangle for this specific proportion, for the height being half the length. So if you have a different proportion, you'd have to rebuild this relationship and get a new expression for that rectangle. The equilateral triangle involves a little bit of trig. So if we look at the equilateral triangle, we know that we have a 60-60-60 degree relationship here. And in order to find the area of a triangle, we need the altitude, and that's supposed to be the altitude. And so when we drop an altitude down here, we have a 30, 60, 90 triangle. And so this base extends all the way from one end of the equilateral triangle to the other. So if we look at that side, then we notice that the side, one edge of that equilateral triangle is in fact the function itself. And in order to get this altitude, we need to take the square root of 3 times just this portion of that side. So sketching out that 30, 60, 90 triangle. Let me redraw that. That was kind of sloppy. Okay, so if we have a that's not any better, but well, you get the idea. If we have our 30, 60 triangle here, then this is s over 2, and this altitude here is going to be the square root of 3 times that. So s over 2 times the square root of 3. And so getting the area then, the area of any triangle is half base times height. The base of the equilateral triangle is that expression, is that side, s. And I'm going to stick with that variable for now. So the base is s, the height is square root of 3 times s over 2. And so simplifying that, you have the square root of 3 over 4. Oops, let me write that a little less sloppy. Square root of 3 divided by 4 times s squared. And again, just to remind you that s is the distance of the entire side, which again happens to be the value of the function itself. So the area for an equilateral triangle is square root of 3 over 4 times the function f of x squared. So if we compare these three, and we can kind of visually just look at the volumes themselves, the pictures themselves, we can see that the rectangle being f of x squared, or 1 times f of x squared, is this is going to be our largest. So that's going to lead to our largest volume. And here's a half of f of x squared. So that's going to be our next largest. So this is going to be our second largest. That's going to be our second largest volume. And then square root of 3 over 4 is approximately equal to 0.433. So this is about 0.433 f of x squared. So this is going to be our next largest, our third largest volume. And pi over 8 is approximately 0.323. So this is about 0.323 f of x squared. So this is going to be our smallest volume if we use shapes of that cross section. For this example, we're going to use the the function y equals 4 minus x squared. That's that function as our base in the first quadrant. So we are going to build solids of known cross sections in this region here. And we're going to build those solids coming straight out of the page at you. So as a bit of a perspective here, we're going to do this for several different cross sections. We're going to start with a square. So here are our squares stacked up, and if you remember from the previous example, our area of our square is side squared, and since the side of one square lies along that base and extends from the x-axis up to the function, that one side is the value of the function itself. And so as we set up the expression to find the volume while using squares of known cross-section, we're going to have our volume, and that volume is just going to be that area function, f of x squared dx. So in this case, it's going to be 4 minus x squared, quantity squared, dx. And we're going to stack these from 0 to 2. And we could FOIL this easy enough and expand it out to find the volume of known cross-section for when it's a square. But I'm going to just use the fint capability on my calculator to get that answer a little more quickly. And so if we, and I'm actually going to use the y equals function too, so I'm going to go ahead and put 4 minus x squared into y1 and grab that function when I do my fint. So math 9 to get fint, and I've stuck the function into y1, so if you remember, I'm going to select vars, scroll over to y vars, grab my function y1, and then I'm going to go ahead and square that function. And we're integrating with respect to x, and we're integrating on the interval from 0 to 2. And so the volume for that is going to be 17.06 repeating units cubed for cross sections that are squares. If we look at the next example, we're going to do the same function, but we're going to use cross sections that are equilateral triangles. Okay, let's get the scrolling feature right here. There we go. Come on. See if I can get that whole triangle on the screen. Stop. There we go. Okay, so to get the volume of this equilateral triangle, we know that the expression for the area of an equilateral triangle is square root of 3 over 4 times the function squared. And so really, as a shortcut, since we've already integrated the function squared, we really could take the answer from part A. And just multiply that times the square root of 3 over 4, because we've already integrated the function squared from 0 to 2. So I am going to go ahead and set up what the integral would look like from 0 to 2, square root of 3 over 4. 4 minus x squared is the function squared dx. But we've already integrated that, and we know that that is 17.06 repeating. So I'm just going to go ahead and say this answer is the square root of 3 over 4 times 17.06 repeating. And then I'll just take this times the square root of 3 divided by 4. And so the volume, when we use equilateral triangles, is 7.390. 7.390 cubic units. For the last solid known cross-section, if we're looking at a semicircle here, we know that the expression for the area of a semicircle is pi over 8 times the function squared. And so if we come up with the expression for the integral for the volume of this known cross-section, it's going to look like pi over 8 times 4 minus x squared, quantity squared dx. And again, since we already have integrated the 4 minus x squared, quantity squared, I'm just going to use that expression. And so let's get that back up on the calculator here. That was 17.06 repeating. And so if I take that down and just multiply that by pi and divide by 8, the area for the solid of known cross-section when it's a semicircle is going to be 6.702 cubic units.